Hey everyone, Big Mac here. Welcome back to part 3 or 2 of my favorite calculus questions answered. So again, this is just part of my list of calculus questions that I had developed over the semester that I was teaching first semester calculus. So let's go ahead and go into the second part here, where I talk about some of my favorite questions from exam number 2. So in this particular section of chapter 2, students had been introduced to the notion of the derivative in terms of the limits. So students were familiar with limits, with what the definition of the derivative is with respect to that, as well as computing the basic derivatives of some functions. We talked about continuity and differentiability, and we explored taking the derivatives of a few functions. So basically like your standard lines and parabolas, your basic polynomial or monomial terms, things like that. So anyway, let's go ahead and look at a question from exam number 2. We have this particular piecewise function here, where it has constants or unknown constants b and k. So what we have to do in this case is find all values of b and k so that the following function is both continuous and differentiable at x is equal to 1. So for when x is less than or equal to 1, it follows a linear function, f of x equals bx plus k. And for x being greater than 1, it goes by the function k squared times x squared. So for this problem, I said calculators were not allowed, and I was hoping that students would finish this question in about 6 minutes' time. So what was necessary for this particular question to happen? So again, we were talking about the function to be continuous at x equals 1 and to be differentiable at x equals 1. So following our basic notations of continuity and differentiability, what this tells us is that as we take the limit from both sides of the function, as x is approaching 1, that the limit from the left side has to equal the limit from the right side, which has to be the same point as f of 1. And then again, going back to our original function, we said that when x is equal to 1, we're still using the linear part of the function. So of course, also to be differentiable at x equals 1, we have to take the derivatives of both parts of the function and then take the limit as x equals 1. That way we still have the same limit, or the same derivative from both sides. So what does this tell us? Well, from our continuity, we know that basically since our limits have to match up, that the limit of our left side as x approaches 1, we just plug in x equals 1, or 1 in for x. So our y value from the left side is going to be b plus k, and then our y value from the right side is going to be k squared times 1 squared. So then we know we have a relationship b plus k has to be k squared, or has to be equal to k squared. From our differentiability, we know that the derivative of our linear equation is just the slope of the line, so just b. And then for our regular parabola coefficient times x squared, we know that its derivative is 2 times that coefficient times x. So for our right side, we have k squared as our coefficient, multiply that by 2, multiply that by x, but again, x has to be 1 in this case. So just plugging x in for 1, or 1 in for x, we now have a second equation, b equals 2k squared. So we now have two equations, two unknowns, that students should be very comfortable solving this system of equations. I set it up so that you can just substitute in 2k squared for b back into the first equation and then solve. This is basic algebra that all the students should be comfortable computing. So of course we get k squared plus k equals 0 once you combine all your terms and everything. So factoring out, that actually gives us two possible solutions. One where k is 0, or the other one where k is negative 1. So since we said that b has to be equal to 2 times k squared, so when k is 0, that means b has to be 0, or when k is negative 1, that means that b has to be 2. So indeed, we actually have two functions that satisfy this inequality. So here I've put up a graph of the function to illustrate what's going on here. So in fact, for our linear part of the function, it follows the equation y equals 2x minus 1, and then for on the right point, or to the right of x equals 1, it just follows our standard x squared parabola. So in fact, we know that that point goes through the through the exact point 1, 1. We have our continuity and we have our differentiability because the derivatives from both sides equal to 2. So of course the other possibility is k is 0 and b is 0. So if we just have a flat x y or y equals 0 function, well, of course it's going to be continuous and differentiable. That's not too interesting though, but it is still a viable solution. So how did students do on this one? Well, not too well. There were a lot of steps that either people just got stuck on, which I'm really hoping they weren't. So about only 20% of the students found the ideal solution, 2 and minus 1. So 2 for B and 2 for B and minus 1 for K. And then only a couple of students recognized that 0, 0 could have been a solution also. What wound up happening was when students had the k squared plus k equals 0 system or equation, I had a lot of students dividing by k. So they found the -1 solution, but then they lost the 0 solution. So I was not happy about that at all. Their algebra teacher, high school algebra teachers, would not be happy with that at all. Of course, there were a number of issues that popped up. One, students had no idea that they had to use a criterion for continuity and for differentiability. A lot of students just did not seem to understand that concept. So I stated that the function had to be continuous and differentiable. So I was trying to clue into students that you had to examine both of these different aspects. However, many students just tried the notion of continuity. So they only had the equation, b plus k equals k squared, and their final answer was all values of b and k such that this is true. And I'm like, no, you didn't figure out all of the required conditions. We also had our differentiability condition reduces that down to just a couple of possible solutions. So I was pretty mad. Another thing that really annoyed me was that we had that, final solution. People that tried taking the derivatives, people tried taking or poking in the continuity thing, there were x's in our final equation. So students did not recognize that they had to plug in 1 for x. We were only interested about the continuity and differentiability at x equals 1, and many students were still not recognizing that. Another bad thing that I saw was that some students actually did develop the system of equations, and since it was not in your standard 4x plus 2y equals 3, y minus 3x equals 8 or something like that, since they had k squared terms in there, I had a couple of students who were like, I don't know how to solve this system. Really? Really? I was very disappointed with those students as well. But again, at this point, I can't help them with their algebra, and admittedly, this problem got bogged down by algebra. And I was only using the algebra just to prove to them that, yes, they need all of these previous things that they've learned. And yet, they still didn't know it. Lastly, some students tried using k as a variable. So they thought, oh, I have to do like 2 times k times x squared, where they were treating k as the variable to be differentiated instead of x. So that messed people up as well. This will be my last question that I talk about for this particular video. So I have a function where we talked about the intro to the derivative. So not only expressing it in terms of the limit and things like that, but also just giving a practical interpretation of these things. Units, and trying to understand what it means for a function to have a derivative. Have a derivative of a particular value. So I had a 3-part question here. Again, no calculators allowed here. So suppose G, capital G, represents the gas efficiency of a vehicle. So if I did mention in the original problem that it was in miles per gallon. So suppose we want to express the fuel efficiency as a function of the speed of the car. So of course the speed of the car being in miles per hour. So we have our fuel efficiency, say maybe it's 30 miles per gallon, 40 miles per gallon, 15 depending on what your vehicle is. And then of course you have your velocities, 40 miles per hour, 50 miles per hour, 60 miles per hour, stuff like that. So my first question is, if G is a function of V, then what are the units of the derivative of G with respect to V? That was like a 6% of the exam question, is that do you understand what these things represent? Part B, I asked for a practical interpretation of what does it even mean if G prime of 40 is equal to 1? What does that thing represent with respect to, with the velocity and the fuel efficiency? So part C, and again for part B, just write it out in words, express it in detail. Physically write out in a sentence, what does G prime of 40 equal 1 represent? Lastly, I offered up this question. Suppose we know that G prime of 40 is 1, g prime of 61 is minus 2, and g double prime, so the derivative of this function, is constant. So my question was to determine the speed which maximizes the fuel efficiency. So let's go ahead and look at the first couple parts. The first two parts, I admit, were pretty straightforward. So, of course, if we're taking the derivative of g with respect to v, that's basically a change of g over a change of v. So, that just follows our standard units notation. So, change of g over change of v is the same units as g over v. So we have miles per gallon over miles per hour. Of course, the miles would cancel out. And being careful with our reciprocals, I had a lot of students who still could not do this correctly. The final answer then becomes hours per gallon. So again, that loses the context in terms of velocity and distance, but that's just proper unit maintenance, so that students understand what's going on here. For part B, when I asked for them to explain what g prime of 40 equals 1 represents, I was expecting something along the lines of this. When we increase our speed, or our velocity, from 40 to 41 miles per hour, we expect an efficiency increase of about 1 mile per gallon. So what this means is we're at a point where as we go faster, we actually get better fuel efficiency. That's basically all I was asking for at that point, and I wanted students to use the numbers 40 and 1. And I had a couple of students who were like, from 40 to 40.1, you get a 0.1 mile per gallon efficiency, and I was perfectly happy with that. Then came part C. So again, I gave this particular criteria where we knew the derivative at certain points, and we were also told that the second derivative was constant. So given this information, determine the speed which would maximize our fuel efficiency. So what I wanted students to think about was, what kind of functions have we seen so far whose derivatives are constants? And, the previous question that I showed you guys was kind of a bit of a hint to that. A linear function has a constant derivative. So then, based on this information, again, these are the only kinds of functions we had really talked about, so that gave the hint that g prime of v had to be a linear function. And we already know 2 points that function goes through. So we're already in good shape for that. So, of course, we know that our fuel efficiency is increasing when the derivative is positive, when g prime of v is greater than 0. And we know that, and intuitively, it's getting worse and worse when our derivative is less than 0. So, perhaps we should try and figure out the place where g prime of v is equal to 0, and maybe that will be our answer. So, looking here at this really quick graph I made up, we know that it's positive when our velocity is 40, it's negative when our velocity is 60, and given the particular data values that I gave, it looks like around 46, 47 miles per hour is when our derivative becomes 0. So up until that point, our fuel efficiency had been increasing, but then after that point, our fuel efficiency is decreasing. So what can we do? We have a linear equation, so, figuring out the slope of this thing, the slope of the line just becomes negative 1/7. Just plugging this into, your y equals mx plus b type situation, we can find the equation for that linear. We can find that linear equation, or of course we just want to know when y is equal to 0 at this point, because that's going to seem to indicate when we stop doing better and start getting worse. So plugging that in, we get v is equal to 47 miles per hour. So because what that represents then is that at 47 miles per hour, that is when our car is reaching its maximum fuel efficiency. Up until then, the fuel efficiency was still increasing, but after 47 miles per hour, the fuel efficiency starts getting worse. So that's where we would have our maximum. So parts A and B admittedly went pretty well. A couple students made some really bad algebra mistakes with the units for part A, and most students understood what I was asking for part B. We had done through examples like that in class, so if you almost just kept straight to the same description layout, you were going to do pretty well. As for part C, absolutely nobody got it. Nobody got it. So I wound up, really cutting off that part of the exam, adjusting my scores because of that. So the thing that I was hoping was that, we had talked about, our functions having a positive derivative or a negative derivative formally we had not gone over the notion of maximization or optimization or minimization, your local extrema, your minima, your maxima. We had not formally gone over of that, but I was hoping that, based on this question, maybe it was a little too expected of me for them to figure this out during a 15-minute test, but I was hoping that they could make a connection that, if the derivative was positive and now it's negative, then the original graph probably had like a maximum point, and they've seen maxima and minima before in pre-calculus, but at this point we had not formally discussed it in terms of the calculus. But I was hoping that at least somebody would make that kind of a connection. And I got some people just saying, it's got to be something between 40 and 61, which is what I was, ballpark hoping for, but nobody was able to even get to the part where they write out the linear equation, partially because nobody understood the concept between a derivative. If a derivative has a constant value, then the function of that original function had to be linear. So I lost a lot of people's attention on that. So unfortunately, that question did not go as well as I'd hoped. But when we started talking about continuity, or differentiability, and maximization, optimization type things, I brought back this question, and it made a lot more sense to students. So I'll see you guys in the next part.